get started by introducing Dr. Michele Barbato, and I might pronounce your name correctly.
It's Michele. It's Italian for Michael.
Thank you, and I'm sorry. Thank you so much for giving us your time today. We really appreciate it. We are recording this session so we can make it available to our other partners and to the community. I know there's a lot of interest right now, especially coming at the tail end of fire season, and how we can mitigate those effects and build more fire resistant and affordable and sustainable housing. So Dr. Barbato is interested in modeling, analysis, and design of structures subject to single and multiple hazards. His research group focuses on the interface between high fidelity finite element modeling and advanced probabilistic methods to develop novel design approaches and structural solutions. These efforts lead to new designs and structures that are sustainable, economic, and safe. They increase community resilience to single and multiple hazards and support societal efforts in climate change mitigation and adaptation. In particular, his wildfire-related research focuses on wildfire risk assessment and mitigation, electric grid hardening, and fireproof construction materials. And he is with UC Davis Climate Research Center. So please take it away.
Thank you. Thank you very much for this opportunity, for having me here. And for this opportunity to talk about some of the work that we are doing at UC Davis, develop and really favor a widespread use of a technology for construction of housing that can put together the benefits of being safe, affordable, and sustainable at the same time. I'll start with a very short introduction on the type of material construction technology, describe some advantages and challenges that are in earthen construction, and then focus more on the specifics of my research that is on compressed and stabilized earth block construction, for which we did feasibility studies in different places, and now we are investigating how to use them for wildfire resistant buildings. There will be also some conclusions. So the topic we are really talking is structures that are made using mainly soil. And this type of construction is something that we have been using for more than 10,000 years. It has a lot of examples all over the world with constructions that have survived well for hundreds or thousands of years. Here I'm just showing some examples that are listed in the UNESCO list of things to save in humanity.
And Dr. Barbato, we're not able to see your screen if you are sharing.
Oh.
Can you try again?
Let me try again to share. Let's see.
Thank you. We can see it now.
Visible. I guess you didn't miss a lot of, there was just a lot of words before, so I'll start from here. So these are some example of relevant historical places that are built with earthen construction. Even now, it is estimated that about 30 to 50% of the world population lives in earth-based dwellings. The difference between these type of structures and what we are trying to do is that we are using engineering principle to design these structures according to safety requirements that are typical of modern construction and design codes. So there are three main technologies in earthen construction. One is cob, that is also called monolithic adobe. This is when soil is mixed with fibers, usually natural fibers like straw, water, and then it is layered in order to build these walls. Rammed earth is a different flavor where the material is put between containers and then rammed into the right consistency from the outside. And then adobe, which really includes any type of brick construction, is when sand, clay, and water are used to make blocks that then are put together using masonry type of construction technologies. So why are we looking at this very old technology for a problem that is very modern? The major reason is this is a material that is affordable, locally appropriate, and widely available. I'm not going to enter too much into the details, but with the right proportion of sand, silt, and clay that are the main components of the, it's possible to use this material for construction purposes almost everywhere. And if we use a chemical stabilizer, generally cement or lime, we can expand even more where this material can be found, it can be used for construction. In addition, soil and earthen construction are naturally resistant to fire, to mold, to rot, insects, pests, termites. So it's a very durable type of material. It is also healthy and natural. It has the property of maintaining naturally the indoor humidity within the goal of 40 to 60%, which is considered the optimal range for human health. It does not produce any volatile organic compounds that could be dangerous for health. And it is eco-efficient and sustainable, both from the point of view of operational energy, as it can reduce the costs in heating and cooling by 30 to 70%, depending on the climate, and from the point of view of embodied energy as not being affected by any firing, it uses very little energy. I see a hand up, Anna.
Yeah, I was just curious whether, I mean, obviously I'm sitting in Tahoe City, California, where the snow load is the critical factor for engineering structures up here. And I'm just wondering if you're going to talk about the engineering and whether this is really something that for I mean, being, you know, totally self-centered, something in my area, actually, it's realistic.
It is. You need to design it for the appropriate loads. I actually have another presentation that I just brought in for this kind of questions to show some real houses that are built in real places under real loads. So let me, for a moment, change the shared screen and show you an example of a house in a place that is snowy. Can you see this image of the house? So this is a house that is built in Colorado at 14,000 feet of height. You see a lot of snow during the year. This is just one of the different pictures of the house on one side of the house. And then the same house on the other side is like that, different period of the year. I use this house very often to show that it looks, these houses are not mud houses, but they look really like good houses. This is some interior of the same house. So yes, if you design it correctly, like in this case, you can use these houses. It's another point that I wanted to make. This is now a pretty high level house, relatively expensive. But the work that we are doing is to really make it possible for everybody to use these houses. Going a little bit stepping what I wanted to present. One of the issues with the earthen construction is that it is used for very high level mentions of the order of few $1 million. An example is the house that Will Smith has in Bel Air, that is a multi-million-dollar mansion that is made of Adobe. And then it is used for very low income or no income people, for example, in Haiti, but even here in the United States, I'm collaborating with a program that is for people that are homeless, and it is designed, that program, to provide tiny homes to people that are homeless and create a virtuous circle of new economy with people that get the house, then start working, and then start producing for the economy. The issue is really everything in between, the middle class, and that has to do not with the technical issues, it has to do more with the inertia in the construction industry, and it has to deal with the lack of formalized research that is presented in design codes that people can look at and say, okay, I can build my house this way. Right now, the only solution that you have, if you want to build your own house with this material, is hire a professional engineer and have every single house calculated with the engineering principle, signed by an engineer, signed by an architect, and that increases the cost to a level that it becomes difficult to build the normal houses. So that was a parenthesis, but that is a very good question that Anna was posing, is, can we actually use it? And the response is, from a technical point of view, yes, we need to go through hoops of bureaucratic issues before we can reach that point. And part of the research that we are doing is providing the knowledge that would make those bureaucratical issues go away. Anna, does that respond to your question?
Thank you. I think it does.
So I'm going back to the presentation, but please feel free to stop me anytime. And if we go beyond and there is something that I cannot present because of time limit, it's not a problem. Another advantage of earthen construction is that once it is properly designed, we have proved that it can provide good resistance to hurricane, tornadoes, and earthquakes. And now we are investigating the performance under wildfires, which I will address toward the end of my presentation. So there are also challenges that we have to resolve and that need to be resolved when designing with these. One of the challenges is that soil is a natural material and thus has a higher variability in terms of properties than other industrial materials. So that's something that needs to be taken into account. It has generally poor durability against wet climates if nothing is done to remove that. And here you can see a test that was run on a cob, no, this is actually a rammed earth wall that was exposed to an accelerated test of wetting and drying cycles where there is some damage at the base of the wall. Another issue is that the material by itself is brittle, which means that when you load it, it reaches its maximum strength and then it breaks in a fragile manner, similar to concrete in a certain way, or to rocks, or a piece of chalk that seems like it's not deforming until it breaks completely. It is also labor intensive. and this usually brings up the cost in places where labor is more expensive. I see there is a question in the chat from Ian. Can you give examples of California jurisdictions that have building standards specifically adopted for earthen construction? This is really relative to building codes. The earthen constructions codes that exist right now are the New Mexico building code. I believe is section 14 of the New Mexico administrative code that is for building of earthen construction. Then there is chapter 21, section 2109 of the International Building Code 2019, which has been adopted by the California Building Code. And so if you look at the California Building Code, section 2109 is on Adobe constructions. And then there is appendix AU of the International Residential Code on empirical design of monolithic Adobe. Both the IBC and the IRC are accepted and adopted by the California Building Code. Even though there is always the need of an engineer to sign even an empirical design, because in theory in California you cannot use empirical design even in a seismic zone D, which doesn't make really sense from an engineering point of view, but it makes it difficult to get permit for this type of construction once you want to use it, because the only thing that is in the code is the empirical design. And so the way that is usually circumvented is going back to the TMS codes on masonry and building the equivalency of the masonry made with the normal bricks and the masonry made with the earth blocks. And that's really the entire code landscape that we have in earthen blocks or in other earthen buildings here in the United States, which applies to California.
Thank you.
Welcome. Yes, I'm seeing a comment from Anne Flor. And that is very correct. The comment is that the biggest issue we have run into trying to use earthen construction is finding someone to build it. And that is a real world issue. It's actually a little bit broader than that, because you need to have an engineer that understands how the construction type works, an architect that wants to use it, then a building crew that knows how to build it so that it is safe, and a local building official that is open-minded enough to accept something that they may or may not have seen ever in their life. And these are all of the things that as a university, we are trying to address, because in addition to doing the research, we are also developing at the same time educational material for our engineers, for our architects, for our building crews, and for local building officials. It takes time, but it is definitely a real world issue that is a problem to use in a more widespread manner, this type of construction. It's so true that we have to run some ASTM tests like E84 on earthen blocks to demonstrate that they don't burn, even though it seems quite obvious, at least to me, that soil does not burn. So why would give it a shape of a block become a problem in terms of physics? There is no rationality behind it, but that's how rules work. And so, yes, finding someone that knows how to build it in California is very difficult. There is a little bit more of knowledge of the process in places like Arizona and New Mexico, where there is more history of these materials and structures. There is a relatively big group in Northern California that is working on cob specifically. But beyond that, it's a little bit difficult to find someone that can do it. So if I can overcome the others, how do the overall cost of construction compare to traditional structures, materials versus labor? This is, Anna, something that I will address with the presentation. And so if it is okay, I'll wait for the slide that shows the numbers to respond to that question. Okay, so you're still seeing my screen, correct?
That is correct.
Okay, so let me continue with the challenges. We actually just addressed those. We have lack of engineering-based design codes. That's all it is available: the New Mexico Administrative Code, the International Building Code, Empirical Design, and the International Residential Code, Code Construction. We need education among engineers, architects, so I went through these items already. There is also another problem that is the widespread perception that this is a substandard choice due to poor performance of non-engineered earthen structures in other places in the world. And I'm thinking particularly to things that happened less than 10 years ago in places like Turkey, where after a strong earthquake, more than 10,000 earthen houses had a very bad performance, causing, unfortunately, loss of life. But the point of it is that a lot of these houses that are having these bad performance are houses that are not engineered, are houses that are built by people that are without a house, and the only material they have is soil. They are usually not stabilized, and they are not designed for things that are beyond the vertical loads, where it's just, if it stays up, it's okay. When there is an earthquake, you need to use engineering principle to make sure that the structure behaves. And if you were not to design a structure made with the concrete or steel, you would have exactly the same bad type of performance. So the problem is not intrinsic in the material, is in the lack of engineering behind the construction. And so our work is developing the engineering knowledge that is needed so that we can design this structure like all other more modern materials. And when that is done, you obtain very nice, beautiful looking, but also very resistant, safe structures. And these are examples that are coming from Switzerland, from Africa. Here, I visited just a few months ago a beautiful earthen house that has been built in Southern Davis in 1955, a house that you would never guess is 70 years old because it's in very good structural condition. And so it is feasible, it is possible, but we are not doing it for all of the other ancillary reasons that are behind it. I want to now focus more on our type of construction, that is the earth block, which is using blocks made with soil. I'm not going to enter into the different details, but the one that we are investigating is called compressed and stabilized air blocks because we are adding a chemical stabilizer like lime or cement, and then we are compressing them mechanically in order to build the blocks and achieve better strength and better durability. These are types of blocks that we can build with the different molds. This is an example of our students making one of these blocks with a machine that we built ourselves in the lab when we started this type of research. And then while you can see that this is quite laborious, we have just bought a machine, an hydraulic machine that does this in a much easier manner. All we really need to do is load the soil into the cart, and the cart automatically send it inside the machine at the right speed, and we can produce about 300 blocks per hour with a crew of 3 people that is using this machine. So much faster, much easier, much quicker. And then some studies on feasibility that will also connect with the question that was posed about costs. So we investigated the feasibility of this type of structures in Louisiana, where we were looking at an affordable hurricane-resistant housing for people that were living in temporary houses or that were displaced by hurricanes or that were living in trailers home. More than 350,000 households in Louisiana were in need of affordable housing after Hurricane Katrina, and we were trying to find a solution for that. In addition, in Louisiana, we had a lot of different challenges. One is the poor soil quality that needs amelioration and stabilization. The weather that is hot and wet, which produces problems in terms of durability, and the strong wind loads coming from the hurricanes. All of that needed to be done in a very cost-effective way, otherwise it could not be used. And so we investigated the problem from a structural point of view, an architectural point of view, and an economic point of view. Again, I'm not going to enter into the details of all of this, but we took soil that was available around the LSU campus, normal soil. We investigated the mechanical properties in terms of compression and flexure in order to identify the amount of cement that was needed to have appropriate strength to be used for construction. And so we found that we needed between 9 and 12% addition of cement for that specific soil that we were using. We wanted to address immediately the problem of durability because in Louisiana, this type of construction is not being used a lot because water and rain tends to wash out soil. And so we did an investigation with the wall that was left outside the campus for 6 months, where we are protecting half of the wall using a stucco made with soil and cement with the same composition as 6% that we are using for the blocks. And as you can see, as expected, the side of the wall that was left without any protection to the water during those 6 months, by the way, we got 2 tropical storms that passed through Baton Rouge, starts having a severe problem after just a few months because the mortar is washed away by the rain. But the other side, as you can see, doesn't show any problem. Not only that, but what we did after this test, we demolished the wall, we took all of the bricks, and we tested them again. And what we found was that actually on the side that was protected, the bricks were getting stronger and stronger because the hydration of the cement was continuing due to the presence of all of that water. And so actually the structure was becoming stronger with time, not weaker with time as on the unprotected side. We did our engineering analysis to find the design that was needed to take the wind loads required by ASC 7, that is the code used for design of structures. Again, very quickly, the way that the design was done was developing these curves. The intersection of these curves with the vertical curves are giving us the thickness of the wall that are needed in order to provide the sufficient strength against hurricane winds. And we were able to do it with our blocks and a 30 centimeters thickness, even in places that are expected to have a very high wind speed. And I apologize if everything is in international units, because that's what publications want, the data. But we are talking about 12 inches thickness walls for Hurricane 5 resistance without the need of reinforcement. And with reinforcement, we can bring that thickness down to between 8 and 10 inches. We also tested these materials against windborne debris impact, and of the material before our designing. As you can see, the 2x4 tested with the wind cannon goes through it like a hot knife through butter, leaving this very scary hole in the wall. So what we did was add fibers and specifically recycled plastic fibers obtained by shredding plastic bottles in the composition. And so the wall is able to stop the missile, not only, but the impact is still so strong that the missile is breaking without penetrating the wall. So again, there is a technical problem, but we can find a technical solution to the problem. This is the slide relative to the economic feasibility. In order to reduce the amount of labor needed, we have a big advantage in terms of material cost because the material is fundamentally free. It's the soil that we have under our feet. The idea is you want to use that, minimize the amount of transportation, minimize the amount of other things that need to be used, which it's also great considering what happened with the disruption of the supply chains of timber lately, where the cost of timber skyrocketed for almost a year, blocking a lot of the new constructions. This soil is locally available, it's natural, so there is no disruption of supply chains that will change the cost of the material. We did this analysis with the cost of labor in Louisiana, and we were able to actually develop a construction technique that is based on mortarless interlocking compressed and stabilized earth block that reduces the amount of labor almost by a factor 2. And under these new parameters, we were actually able to build, or at least to design a house, the cost of which would be lower than the cost of an equivalent approximately 1,000 square feet house in southern Louisiana. Which is responding to part of the question of the overall cost that Anna was posing. Now with the additional labor cost in California, we are doing the same exercise and evaluating what is the different cost, and we have found that the cost would be increased by a factor between 10 and 15% on the structural side of the house, which usually is about 25 to 35% of the overall cost, because the other costs are plumbing, heating, cooling, finishing, and all of the other things. So hopefully this responds to the question about the cost. we can bring the cost down so that the differences are not being a point that stops everything else. So as I promised at the beginning, I want to go to talk about wildfire, and I don't need to discuss probably too much about how dangerous and how much risk we are associating with wildfires. We can see what is happening in California. The number of structures that are damaged or destroyed by wildfire is increasing, I would say, exponentially. The number of confirmed loss of life are extremely well correlated, unfortunately, with the losses of houses, much more correlated than with the acres burned of a wildfire. The issue is that we are having two double whammy on us in terms of wildfires. On one side, the hazard is increasing because of climate change. So we have drier seasons, longer wildfire seasons, higher hazard connected with having large wildfires. And we are also increasing our vulnerability because we are building more stuff in the wild and urban interface. So you have that your risk is really increasing due to the hazard and the vulnerability, and risk is the product of the two. So we need to do something about it. What we are doing right now is developing standards that are making the structures ignition resistant. It means that it's difficult for a structure to start burning. This is because everybody considers the cost of a fireproof or fire-resistant house too high to be taken. And that is assuming that the only solution that you have is building a house that is made of concrete or concrete blocks. But with using soil, we can actually bring down the cost so that the two costs are comparable. Here is just a little summary of the major items in Chapter 7A of the California Building Code, the chapter for wild and urban interface. I'm sure that you are very familiar with all of these. And with the concept of defensible space, with the three different regions, two that are actually mandated by law, and one that is currently under development, the so-called Zone 0, that is 5 feet around your house, where everything should be non-combustible and everything should be far from the house. And then there is Zone 1 and Zone 2 that are reduction of fuel load or removal of fuel load. So we are trying to use this material so that the house itself does not burn. We did some preliminary tests, and this is really more for showing than for data, but we are eating the earth block that we are building and the typical 2x4 that is used for construction with a propane torch at 3400 Fahrenheit. And you can see the difference of performance. On one side, the wood is completely torched and burned and charred. And on the other side, all you see is a little change in the color of the material. We have actually done tests that are more scientifically based, where we have heated for different times and at different temperatures our blocks. These are two blocks, one as produced and burned, and one after 7 hours in a furnace at 1800 Fahrenheit. And our preliminary results are actually showing that up to a certain temperature, the blocks become stronger, because the wildfire is producing the effect that you would have in a kiln by firing this material and producing fired clay blocks instead of unfired clay blocks. Up to about this temperature of 1800 Fahrenheit, our blocks are performing well. Then with temperature that are going above 2200 Fahrenheit, you start having a reduction in the strength of the materials, production of microcracks. And if you keep increasing the temperature, you reach a point where the material is glassifying and then melting. But that's kind of expected. And anyway, the temperature reached in wildfires rarely are above 2000 Fahrenheit, and definitely not for 7 hours continued at that temperature. We are doing additional research. We are checking what is happening to these blocks at different temperature and then testing them in compression, flexure, and durability. We want to test also what happens when there is a differential temperature. And then we will end up testing a wall where one side is exposed to the time temperature profile that is in the code, and then subjected to the thermal shock produced by a hose of water typically used by firefighters. Some other considerations that need to be done is when you look at the embodied energy of a light frame wooden house and an earth block house, it may seem that the two types of constructions are equivalent. However, that equation changes a lot once the wooden house burns, because the production of CO2 that is coming from a burning house, and this is without considering all of the toxic material that will burn with the house, it makes it much more similar to the emissions of a concrete block house than the one of an earth block house. And so there is an additional component in terms of greenhouse gases emission that should be taken into account when designing these different type of structures. Finally, a house that is built correctly with soil can have easily a 100 years design service life. And that is in contrast to the wooden houses that have generally a design life between 30 to 50 years, at least nominally. But in reality, the average design life before the cost of renewing the house becomes too high is around 35 years for a normal light framed wood house. I would like to wrap up because I think I'm beyond my time already, but there are some initiatives that are using for the greater good this type of construction. The Good Earth Lodge was an initiative for the Crow tribe in Montana, where they built, the tribe actually developed the plant and built houses for the members of the tribe. There is a program that is running in Scottsdale, Arizona, that is called Brick by Brick, where the homeless people are helping each other by building tiny homes to reduce the problem of homelessness. And then there is a program in Haiti called Welcome Home Haiti, where they have developed a plant for building bricks. And they are building churches, schools. They built more than 700 new houses for people that were homeless or were living in this type of dwellings, which have difficulties to define home. And they are also giving job to 100 people in the community. So renewing completely the outcomes for that community. I don't know if I really need to go through this conclusion, but fundamentally, earthen measuring has the capability to be an affordable, safe, and sustainable technique for construction of houses and low-rise buildings. And considering that we are expected to need about 2 billion new homes in the next 60 to 80 years, this is really an important part of our fight to make quality of life better while ensuring the sustainability of what we are building. And so some acknowledgements that I have to provide to the funding agencies that gave the money to do this research, but also to the many other people that worked with me to present, to develop these results. And I'll be very happy to respond to any question you may have. Thank you very much for having me.
Great, thanks so much, Dr. Barbato. Does anyone have any questions? Additional questions, I should say. I could ask one. So in a nutshell, why isn't it used a little bit more extensively, I guess? I see that it's limited to some specialized projects like the ones you discussed, but why not? Why isn't it used for, I guess, offices, more offices, home buildings?
So actually, the way that this material is used is for high-end houses and for very low-end houses. And it has been used also for official buildings. So there is a beautiful school built with rammed earth in Glendale, California, which was the first gold LEED building in the region when it was built, I believe, in 2012. So the issue is really why it's not used for that intermediate group of houses that affects almost everybody else, the middle class, to use a term that is maybe overused, but I think is appropriate here. And there are several reasons that are mainly implementation-wise. The absence of code that are easily used, the fact that engineers and architects are not taught about this material in their curricula, the fact that building officials have most likely never seen this unless they live in New Mexico or in Arizona. These are all practical problems that make it difficult to use this type of construction.
So it's really a lack of knowledge that's basically preventing it? Okay.
It is a lack of knowledge, and it is a lack of knowledge that is formalized in the same way as it is formalized for other construction materials. It comes also from the fact that while for concrete, reinforced concrete, steel and timber, you have trade associations that have spent quite some money in developing the research and putting it in the format that is needed so that it can be integrated into codes easily. There is nothing like that for earthen construction. It has always been a very bottom-up type of work, and when the money went into industrial materials, everybody wanted to make money. And this type of construction has been, in a certain way, lost in the type of vernacular options that we have available.
Do you know if it's been used for affordable housing projects anywhere?
Yes.
Okay.
It has been used in several contexts. Generally, when labor is not an issue, is the go-to solution, because the big cost of it is labor, and people are extremely enthusiastic to build their own house, and so this is the actually easier material to use for that kind of application.
Right.
In cases like the one in Scottsdale, Arizona, where federal funding was used to start the operation, now they can do it at very low cost. Actually, they are building houses at half the cost than normal houses for the homeless people. But the first investment is what makes it difficult, even from the point of view of a builder. You need to invest quite some money to get the machine, teach everything to your crew, and there is the uncertainty of will I be able to build it if I don't get a permit. And so that's another issue that is not really technical, but is the issue that that is making it difficult.
So a regulatory hurdle, the prospect of kind of working with an unregulated technique that could cause a problem. I see. Okay.
Exactly, because you don't find who is building it, and you need to have an engineer that is designing every single individual house as the current codes is set up. Instead of having one drawings that can be repeated a few thousand times. You can imagine how much that increases artificially the cost of things.
Gotcha. Okay. Well, thanks you so much, Dr. Barbato. Does anyone have any final questions? Oh, Anne, I see your hand up.
Hi, thank you. Have you built any case studies or test buildings with your brick making machine?
We have not built any prototype yet with our machine. We are starting from the basics, like developing the actual format for testing the blocks, for testing the mortar, and then growing to small panels. And we have the funds to reach the level of a wall. We are always looking for funding to actually have a prototype that can be instrumented on campus and then tested under the different possible conditions, including wildfire. But as you can imagine, there is a cost associated with doing any type of research. So you need to also, in that case, build little by little, put more proofs out, and then hopefully we will reach a critical mass and we can start building prototypes. And once the prototypes, as I expect, will perform as well as all on the indication we will have a much higher chance to actually see it implemented, at least in an experimental way, for example, in a project for affordable housing somewhere in California.
Reason I asked, I'm working on a carport inaccessible dwelling unit for a professor at UC Davis who has acreage outside of Davis, and I've been trying to get them to either do something out of straw bale or earthen construction. One of their main motivations is for it to be fire resistant, and something like that seems like it would be a good.
Who's the person?
Richard Michelmore, he works in the genetic department.
Okay. Be interesting to reach out and see if we can convince them.
It could be an interesting conversation.
Yep. Thank you.
Thank you so much again, Dr. Barbato. We really appreciate it. And if anyone has any follow-up questions, please feel free to contact Christina and I, and we'll get them off to Dr. Barbato for you.
Yep. And also you should have my my email.
Yes.
And also I have difficulties to hide myself online. I used to say that likely I don't have any disgruntled ex-girlfriend, because they would be able to find me very easily. Thank you.
Wonderful. Thank you so much again.
My pleasure. And have a great rest of the day.
Wonderful. Thank you. You too.
Bye.
Bye.
Thank you.
Bye. Thank you so much, Dr. Barbato. I really appreciate the knowledge that you lent to us, and it's so great. I hope we can help get more education out there so we can see this build more.
Yeah.
Thank you.
Bye.
Bye.